Oh shoot, where's my boy? Where's Lamech? He didn't he's not here to tell me to get started. All right, whatever.
One and two.
Oh man, what a late comer. All right, so let's get started. We are recording. This is lecture 8. We got 4 more lectures to go and 2 more quizzes. So I'm just reminding you guys, quiz 2 is tomorrow. It covers sequences. This was 10-1. It covers geometric series, which is like mostly 10-2. And then these 3 topics were like from 10-2 and 10-3-ish. So why do you have so many people? There's like 28 people in here. All right. So yeah, our quiz 2 is tomorrow. Same format as the other one and the midterm, right? So make sure you're showing your face, make sure you hand it in on time, yada, yada, yada. I went over last class what was going to be on this quiz. So, I mean, you can just read it off the screen here. I'm not going to go through it again. Homework 5 is also due tomorrow, I think. Can someone confirm or deny?
Yeah.
Yes, it is.
Okay, cool. So homework 5 is due tomorrow. And then quiz 3 is next week. It's going to be on Tuesday, I think. I think the 28th. When is the 20th? Yes, it's going to be on the Tuesday. And then your final for this class and for some of your other classes is next Thursday. So we got like a week and some change left. I really hope you guys just push through, okay? It's going to be a hell of a week. So just make it through, guys. Today, we are going to we're going to finish up 10-3 with something called the limit comparison test, or LCT for short. And then we're going to talk about something called absolute/conditional convergence. I'm going to skip something. I might do it in the video or in a video just so that you guys have it. And then if there's time, we can start ratio test, which is like, I think it's the last like test. So yeah, so we covered a lot of tests so far. Let's just get started by kind of reviewing like the tests that we've done so far and what I expect you to know for the quiz, and then like other things. Okay, so first and foremost, so let me just write tests so far. All right. The first one we talked about, right? The first type of series we talked about was geometric. So it's not called like the geometric test. They're just called geometric series that have like properties that you should know, right? Geometric, it has the form AR to the N. Pay attention to like the index, right? We talked about this, right? Where it starts will determine your A value. If the absolute value of R is less than 1, it converges. And then if the absolute value of R is greater than 1, it diverges. And then if it converges, then it converges to, A over 1 minus R, where A is the first term. It is the first term. Okay, so, actually, I should, some books you see, because, sometimes, because this isn't always A, right? So we talked about this last class, so always pay attention to that. That's geometric series. It's the one that tells you what this series actually converges to, if it converges, right? So, and it's the only one that does that. The next thing that you guys learned was the nth term test, or the divergence test. Oh. Okay, it says, given this guy, if the limit of a sub n as n goes to infinity does not equal 0, then you know that this series diverges. What's going on with Lamech? Trying to join, we can't. All right. Okay, divergence test, a big pitfall of that one is people think that if it does equal 0, then it converges, but that is not true. That is not true, right? So it's really important. The divergence test is only for divergence, all right? Next, we learned the integral test, right? Does anyone remember like the 3 things that you need to have for you to run this test? Anyone want to?
It's
Positive,
continuous,
continuous, decreasing.
it's decreasing, and it's positive, I believe.
Okay, but like what? What has to be positive, continuous?
The function,
And where did this function come from?
it comes from the geometric, it comes from the series.
It comes from the series. Yeah, it comes from the sequence, right? That's given, right? So given this guy, create a positive, continuous, decreasing f of n if the integral of that function, I guess I'll use dm. This is kind of weird. I'm like shorthanding everything. I hope you guys understand everything. Just let me know if like you guys don't understand something. But if the integral, whatever the integral does, if the integral diverges, then the series diverges, and then like vice versa. If the integral converges, so I'll put slash converges, then the series converges. All right. So basically, the series follows whatever the integral does, because they're so closely resemble to each other.
John, what was that end part you wrote? Positive, continuous, decreasing. Oh, f of n, like the function. Okay.
Yeah. You create it says create a function that resembles the sequence.
Could you scroll up for a quick second? Just want to get that last part in geometric. Okay.
It just says what it converges to, the geometric.
Okay, got it. Thank you.
And once again, guys, if you missed something, I always post up the video. So what was I saying? Integral test. And I think that's pretty much it. Now, this isn't a formal definition of integral test. I just think that this is like a more like reader-friendly type of way to kind of interpret it. If you guys have your own way of like kind of interpreting, by all means, use your own way. But a big important thing for this one is if the sequence, I think I said this last class too, looks integratable, use the integral test. So it's like if it looks like you can use u sub on it, or if it looks like an integration by parts or partial fractions or like one of the other integration methods that you've learned, chances are it's probably an integral test. But then again, like, if it looks like this, you wouldn't use integral test. You could use integral test, but there's a much faster test for you to use, right? And that is, anyone?
Good.
Nth term test.
Well, it doesn't. Nth term test is inconclusive on this one.
DCT, direct comparison test.
No.
Oh, the geometric one?
Nope.
Diverge.
Oh, wow.
P-series.
Oh.
Out of the integral test, the P-series was.
Oh yeah.
The idea of P-series was born. Okay, so it's like they did the integral test and they were like, oh, I noticed that whenever series are resembled to that, right? So if given something that resembles this from, I don't know, it doesn't have to be one, but if it resembles this, you don't have to do the integral test every time anymore. You can just stay. And if P is greater than, or no, it's just greater than 1, converges. And then if P is less than or equal to 1, it is divergent. Questions so far? How many have we hit so far? There's 1, there's 2, there's 3. I guess I don't like counting pieces, but sure, 4. Then we talked about direct comparison test, or DCT. And this was something that we talked about last class. I kind of flubbed at the end. I apologize for that. I messed up with like some definitions with like A sub n and B sub n. So we can kind of like revisit that again today and just talk about it a little bit more to lead us into the one after this. But yeah, DCT, it says A sub n less than B sub n. And this kind of breaks down into two scenarios, right? A convergent case and a divergent case, right? I drew the pictures and everything last class. I drew the graphs, and hopefully there's a better understanding of this. But basically, if you have A sub n less than B sub n, and it's the convergent case, you want B sub n to be the one that you know, and you want it to converge. Because if the one that's above converges, you know that the stuff, anything below, will converge also. The whole like my brother's in the house thing, right? So, and then the divergent case, it's like the reverse a little bit, right? Still A sub n, B sub n, but like in this case, you want this one to be the one you know, and you want this one to diverge, right? Because if something is too big, then anything above it will also be too big and also diverge. Are we like okay with that idea yet, or are we still like I'm not seeing it, John?
I understand.
Okay. This is gonna be important for today too, because we're gonna talk about the LCT. So what was that? Or like a fifth one? So 1, 2, 3, I guess 4, 5. We have the LCT to do, so that's 6. We have alternating series test to do, 7, and ratio test, 8. So for quiz 3, you are gonna be required to know all 8 tests, okay? And then some extra stuff that we're gonna get to. So let's get started with today's stuff. We're gonna finish up with LCT, which is the limit comparison test. The limit comparison test. This is another type of comparison test, but this is one that you use in very specific scenarios. Okay, let me throw something at you guys. Let me throw an example at you. Let's try this one. 1 over n squared plus 100n plus 4. Something like that. Ew. Okay, how would you prove convergence / divergence on this one?
Maybe try the integral test, partial fractions and everything.
Remember, we want to pick a test that's like the easiest and fastest test to use. We could use integral
Then you
test
could
on
use the
this.
divergence test first.
Okay, fine. Well, if you use the divergence test on this, it looks like the sequence is going to 0, so it's inconclusive. All right, so we need another test.
What about the comparison test?
Which one? And who said that?
Oh, me, my bad.
Oh, Carlos, got you. Okay.
The one where you compare to another, I forgot the name of it, man. Where you compare to the one that's like less than it.
Direct
So
comparison.
So like compare to 1 over n squared.
Okay, so you just said a lot of information there. So yes, we want to use the direct comparison test. We want to try to make a direct comparison, right? And it looks like you're saying this resembles, well, the top is 1 and the bottom resembles n squared. Why isn't it n squared plus n? Why didn't we do this? Doesn't that resemble more?
I mean, I guess, but I thought since like n squared was like bigger.
Yeah. Okay. So I was trying to trick you, Carlos. I'm sorry. Sorry, not sorry. But yeah, you wanna pick the highest power that's available on the numerator and the denominator. This is how you create your B sub n. I keep doing that. This is how you create your known series, right? Because if I tack a sum sign on this, I know how to prove convergence or divergence on that. I don't know how to prove convergence or divergence for this specific case yet, right? Do you see how I'm like using logic here, right?
Yeah.
So I'm using something that I know to tell me about something that I don't, right? So I know, so I'm going to label this. I'm going to call this B sub n, and I'm going to call the one that we started with A sub n. Did I have to do that? No, I could have been like, okay, this is A sub n and this is B sub n, right? Like that part's not really important. I know some of you guys are really hung up on like definitions and stuff, like theorems that they give you in the book, but it's better to understand like what it is that we're trying to do, right? So I think it's better if you just label it as like the one that you know and the one that you don't, right? So, and then like put the labels on. So once again, I'm gonna put this as A sub n, and this one as B sub n. So I know, so I'm gonna start like writing stuff that I know. So I know the sum of B sub n converges by P series, right? I'm kind of like building my case here. I'm building my argument. So I know that the sum of B sub n converges by P series. If something is convergent and I'm trying to use DCT, well then what needs to be true for A sub n, the relationship between B sub n and A sub n?
Then if B sub n is convergent, then A sub n is also convergent since B sub n is greater than A sub n.
We want B sub n, so we want B sub n to be greater than A sub n. We're not really sure at this point, right? So watch. I'm gonna replace the stuff. This becomes 1 over n squared, and we're like, and what is it? Is 1 over n squared plus 100n plus 4. And we want this to be true. If this is true, if this is true and all equivalent forms of this is true, then we can go say like, our brother's in the house, okay? Because I'm just running out of time here. All right, so watch. I'm gonna use algebra here to show that this is true. What do? I'm gonna multiply both sides by the common denominator because clearly you guys don't like fractions. So I'm gonna show it algebraically here, right? So I'm gonna multiply everything by the common denominator, which is 4, right? On the left side, what am I left with? I'm left with n squared plus 100n plus 4. And then on the right side, I'm left with n squared, right? You can even take this a step further. You can even take this a step further and say 100n plus 4, is that greater than 0? Is this greater than 0 for all n that fits in our index? Yes,
yeah.
Right? So because if I plug 1 in for n, yes, 104 is greater than 0, and then so on and so forth. So because it's kind of like a domino effect, because this is true, this is true, this is true, and this is true, our initial like statement. You see how it like kind of like dominoed backwards because of math, right? So what do we say? Since the sum of B sub n is greater than the sum of A sub n, and the sum of B sub n, we said converges, we can now say the sum of A sub n also converges by, what did we just do?
Direct comparison test.
DCT. This is the proper 100% formal write-up that I am looking for on your quizzes tomorrow. Should you use DCT? Okay, you cannot just say this statement, the box statement, without your supporting work, everything that's above this. Does that make sense?
Yeah.
Okay, so pitfalls, common pitfalls, not labeling, right? So make sure you label it, and those labels are consistent. Another pitfall is like this step. They just stop here and they don't fully show it, right? If you stopped here, that would have been fine. I just took it one extra step to kind of make a stronger statement. And then you need to have your justifications and all that stuff written out, along with like the test that you used, and then like why B sub n converged. We said that in the beginning. We said, we said that up here.
At the top, why did you write OCT?
Oh, I'm getting there. I wanted to just do another DCT example with you guys, just to like make sure you guys are good.
Oh, okay, got it.
Okay, all right. But we're getting there, buddy. So watch. I'm gonna tweak this problem, oh so slightly. Watch. Ready? So example 1, tweaked. Right? I'm gonna tweak this example oh so slightly. Ready? N equals 1 to infinity. It's 1 over n squared minus 4n. What was it? Plus 4? What was it? It was
Yeah, it was plus minus 100 and plus 4.
That's 100n. I'm sorry. So do you guys see the tiny little change I made?
Yeah.
I put a minus 100n. And what that minus is actually going to do is it's going to screw things up for us. So watch this. Once again, this resembles 1 over n squared, like yada, yada, yada. I'm just going to go through this real quick, right? We wanted a sub n to be less than. Come on.
B sub n is no longer going to be greater than A sub n.
Okay, man, like you must be great at parties, man. You just ruined the whole surprise and everything. Gosh, just get there, dude. So you get this 1 over n squared minus 100n plus 4 less than 1 over n squared, and then we like multiply by the common denominator. We get n squared. Is this less than n squared minus 100n plus 4? And you get to this logic statement, and you're like, oh, poopy, this is not true for all n greater than 1, right? If I plug 1 in, what happens?
If you plug 1 in, 1 squared, 100, it's going to be negative on the right. And then
You're going to get a false statement. You're going to get a false statement. And this is an example of where DCT does not work. I'm sorry. I know you guys love DCT and all, but DCT is not 100% like effective. Okay? LCT is 100% effective. It just takes a little longer to do. So that is like the advantage and disadvantage. And what hopefully I answered, oh my gosh, who asked? Was it Joanna? I think it was Joanna in the beginning. Like on the quiz tomorrow, if you choose to use LCT, it should always work, like from beginning to end. All right. So I'm just letting you know. So going back to this means I can't use DCT. So I need something else. Let me show you the theorem. What page is on 580? The theorem they give in the book on LCT. So it starts off by saying let A sub n and B sub n be positive sequences, which is duh, right? And then assume the following limit exists. So L equals the limit as n goes to infinity. We're going to take A sub n over B sub n. Come on. Load. Okay, there we go. 3 possible outcomes happen with this L value, okay? 3 possible outcomes happen with this L value. So the first outcome, which is probably the most common outcome, if L is, they say greater than 0, but infinity is greater than 0, right? So if L is in between 0 and infinity, meaning if L is finite, you get a number, okay? If L is a number, right? I do not like the wording. Whatever. Okay, then the sum of A sub n converges if and only if the sum of B sub n converges. I don't like the wording of this thing. Is there ooh, better wording here. Okay, let me get rid of that. I'm sorry. So keep the first part. If the limit is finite. Sorry. Why is this not erasing? Come on. Erase. Come on, you stupid pen. All right. Okay. So if it's finite, then both series either converge or diverge. I like that phrasing a lot better. The second case goes if the limit is infinity, and the sum of A sub n converges, then the sum of B sub n converges. And then the last case is if L is equal to 0 and B sub n converges, then A sub n converges. Okay, so it looks like a lot here. I know it looks like a lot. These second two cases, they're kind of like, it depends on how you define everything. So let me just kind of break this down. Let me break down the first case, so that it's a little easier to like digest. Okay, and by all means, please ask your questions if none of this is making any sense. Okay, so let's kind of look back at what we're doing here. Like what are we doing at this step? What are we doing here? Can anyone?
For the first one, wait.
What I just highlighted right here.
We're taking the limit of what we know and what we don't know.
Ooh, wow! Who said that? That was very.
I said that, Ali.
That was very good. Yeah, Ali. Yeah. And you notice in the definition they gave us, they're not telling us explicitly which one is the one that we know and which one is the one that we don't. Right?
Mhm.
They're just saying if we get a limit and it's finite, then that means both of them will do the same thing. That's what this second part is saying. Whatever A sub n is, B sub n will do, or whatever B sub n is, A sub n will do, regardless of which one's known or unknown. Does that make sense?
Okay.
Mhm.
And I hope you guys can take it one step further, because we're going to do this with the ratio test too. But like what we're doing here, what we're really doing here is we're looking at the growth rates of the two sequences, right? I have one sequence that's growing like this way, and then I have another sequence that's growing this way. Well, if I put them over each other and see what's happening, right? As we go to really, really large numbers, and if they kind of become one number, like a finite number, that means that they're both growing in a way where eventually it'll be like a constant, like where eventually they'll be growing at the same rate.
Okay.
Anything? Did that no? Was that like a mind blow? That was supposed to be like a, oh snap, that kind of makes sense. Like think about it. If I get a limit of 2, okay? Let's say I took the one sequence, I put it over the other sequence, and it equals 2. What does that mean? What does that mean the relationship is between A sub n and B sub n?
That they both do the same thing.
Can you be a little bit more specific?
That they'll both reach 2. Increase.
It's not that they both will each reach 2. It means that
They both converge and diverge.
But like why? That's the point I'm trying to get you guys to think there. It means that A sub
You mean
n,
that both growth rates are positive? That means that both.
it means that A sub n is growing 2 times as fast as B sub n. Right?
Yeah.
And so like, okay, think about it like this. You guys drive, right? Maybe.
Yeah.
I mean, I know you guys aren't experienced with driving, but like you guys drive, right? Imagine a car that's like 10 feet, 10 feet in front of you, but both of you are going the same speed limit, right? Both of you could be going like 65 because you guys are safe drivers, okay? So both of you are going like 65 miles an hour, but there's 10 feet in between you. That's what I'm talking about. That's what that 2 represents. That's what that constant represents. Yes, there's space in between you, but both of you are going at the same rate. That's why it canceled out and became a constant. Does this make sense?
Yeah.
If it was 1, that means both of you are going at the same rate and are at the same spot eventually, because we're going to infinity. Right? Does that make sense?
Yeah.
Yeah.
Okay, cool. So that's the first case. That's the first case. Like, so whatever A sub n is gonna do, B sub n will do too. So it's like, if your A sub n is the one that you know, okay, that's great. Then the B sub n will follow A sub n. Or if the B sub n is the one that you know, then A sub n will follow B sub n. So in this first case, yeah, the order doesn't matter. How you set up the limit, it really doesn't matter, so long as your final result is a constant. Is that okay? Does that make sense? Cool.
I also wanted to add this. That the reason why the first statement why you because like I was thinking about this in the beginning for a few seconds and I was like it's the reason why I said that let A n plus B and B sub n be positive sequences is so that the limit does not did anybody even hear what I said?
I'm trying to understand what you're saying, man. I didn't
No,
get
I'm
it.
saying like the reason why the A sub n plus B sub n need to be positive sequences.
Well, yeah. So I mean, we've only been playing with positive sequences really for this whole thing. The next part, the 10-4, because we're in 10-3 right now. 10-4 talks about what happens when there's negative terms. So we'll talk about that when we talk about 10-4. The other two cases, they're kind of like they depend on. Oh my gosh, how do I say this? The other two cases depend on how you define A and B. So the first case, it didn't matter how you define A and B, right? You could just choose one to be A sub n, the other one to be B sub n. Take the limit, find a number. If it's a number, then they both do the same thing. With 2 and 3, it depends. So let me talk about case 2. So if L is equal to infinity, right? And we know L is this guy right here. Okay. So let's kind of dissect this a little bit here, right? If L is infinity, what needs to occur? What needs to occur? Let me finish my sentence, man. What needs to occur? What needs to occur for L to be infinity?
A sub n needs to be infinity.
Well, can you be a little bit more specific than that?
Oh, like
what about B sub n?
B sub n also could be infinity, but yeah.
So
doesn't B sub n have to be really, really small?
It has to be greater than 0. Greater.
Okay, so you got to be careful here, right? If they both go to infinity, that's kind of indeterminate, doesn't really tell you anything, right? This is why growth rates are so important. In fact, hopefully this gleans a little bit about L'Hopital's, right? Taking the rates of the top and the bottom. If you get infinity over infinity, that's useless. You want to see clearly that A sub n is growing faster than B sub n. That's the only way you're going to get infinity.
So
you guys see that? The top needs to grow faster than B sub n. That's the only way, right? So going back to the car thing, right? The only way for one car to be ahead of the other one is if they speed up and get ahead and constantly speed up while the other one doesn't really do that. Or the other one doesn't speed up as fast as the other one. Am I making any sense here?
Yeah.
Right? So the only way for L to be infinity is if A sub n grows much faster than B sub n. Or, does that look familiar?
Yeah.
What happens when you have a converging converging series, and it's greater than another series?
That the other series also converges.
Yes. And that's what it's saying, right? The second part is saying A sub n needs to converge. If A sub n converges, then you can conclude that B sub n converges because A sub n is growing faster than B sub n. Is this too much for you guys right now?
No, I understand.
Like, I don't know, John. This is too much for me. It's 1:44 on a Monday, and I can't.
It makes sense, but could you show an example showcasing this, like number 2?
I was hoping you wouldn't say that. Number 2 and 3, it's kind of hard to
Find one that's not the derivative, not the direct comparison tests, and
exactly, yeah. It has to not work for DCT, and then like it has to fit 2 and 3. So this is what I was saying. Like number 1, this is gonna happen like 90% of the time. Number 2 and 3, they're just there for like just to fulfill the definition. You know, they want to cover all their bases. Number 2 and 3 are just more of like a logic piece. Really, you're gonna come across number 1 a lot more, to be honest.
I guess could you just explain the converging part again? It's like the comparison, if that makes sense.
Do we understand this piece that that if the limit is infinity, you can conclude that a sub n is greater than b sub n.
Yeah.
That needs to be true, right? Okay.
100%.
So if you understand that, then this is true. Then a sub n is greater than b sub n eventually, right? So I can tack these on and be like, if a sub n converges, b sub n also has to converge.
And the order doesn't really matter because it still stays the same.
It kind of does, right? Because what happens if b sub n is the one that you know?
Oh, so the second part kind of goes back to the definitions we like determined earlier.
Yes.
Like the idea.
This is what I was saying, that those pictures are really important. Putting the stuff under or over.
Yeah.
So it's like it depends. Like number 2 and 3 depend on what you define as convergent or divergent.
Yeah.
How are we doing here?
good.
Okay, right. So like for the second definition, right? So if a sub n converges, then b sub n converges. But you can also say, like, this is like a 2a or 2.2, whatever. If b sub n diverges, then a sub n also diverges. I'll say that one more time. If the limit is infinity, that means a sub n is growing faster than b sub n. And if b sub n diverges, then a sub n also has to diverge. So you actually get 2 for 1 kind of thing.
Or a copy of the direct convergence test.
Yeah, essentially it's like reiterating the direct comparison test.
Hey John, so if the denominator goes to infinity, then a sub n also goes to infinity?
Oh no, that's not what I'm saying. I'm saying all we're saying is that a sub n gets to infinity faster than b sub n.
Yeah.
Like b sub n could go to infinity, or b sub n could go to a constant. But we know, because with this statement, with the limit being infinity, we know that a sub n goes to infinity faster.
Okay. But then if the limit is infinity, but b sub n is b sub n is larger than
if b sub n diverges.
Okay.
This conclusion, this infinity conclusion, leads to this conclusion. Right? And we know that if we're given this second conclusion, that if a sub n converges, b sub n converges. We also know if b sub n diverges, a sub n diverges. But it kind of depends on the situation, like what you're given and what you're trying to prove.
Okay.
Similarly for the third case, if L is 0, what can you tell me about the relationship between a sub n and b sub n? Just try and get there.
That means a sub n has to be 0.
I'm sorry, what?
That means a sub n has to be 0.
No. This if L is equal to 0 is telling us about the rates between a sub n and b sub n.
And b sub n faster.
So b sub n is growing faster than a sub n. B sub n is getting to a larger number and a sub n just can't keep up. Right?
Yeah.
And if this is the case, then everything kind of flips, right? If let's say if b sub n converges, a sub n converges, right? Because it's greater than a sub n. And then if a sub n diverges, b sub n diverges. How are we doing? Did I just confuse the crap out of everyone? Oh no.
I feel like I understand why they gave us the name now. comparison test and well, like they're like related to the direct comparison test and everything. They all just
Also,
follow.
the fact that it's called the limit comparison test, right? We're
Yeah.
using limits because we want to see the growth rates, as opposed to direct comparison tests where you're directly comparing to.
It's like you use the limit, and then after you find the limit and everything, you then use direct comparison test and everything.
In the second and third case, yeah, pretty
Yeah.
much.
Yeah, the first case is just
That's right.
So with that being said, let me do the example. Let me finish off the example that I put up there. What was it? It was 1 over
1 over n squared minus 100n.
Okay.
wait, 100n was the
Plus 4.
There's
Okay.
a question in the chat.
Oh, I'm sorry. Are cases 2 and 3 going to be on the test? I don't know. I don't think so. I mean, the ideas of 2 and 3 are going to be apparent, but I don't think there's going to be one where the limit goes to like 0 or infinity. I'm pretty sure. So let me show you. So on this one, I'm going to call this one a sub n. And we already defined our b sub n, right? It's going to be 1 over n squared. Do I have to explain that, or are you guys good on that now?
We're good.
Once again, you look on the power on the top, power on the bottom, put them over each other, simplify. We know the sum of b sub n converges by p series, right?
Yeah.
And we just said before we can't use DCT, all right? So we're going to use the LCT. We're going to use the limit comparison test. So I'm going to take the limit as n goes to infinity. Like I said, it shouldn't really matter. It should not really matter the orientation, okay? How you do, if you do a over b or b over a, all right? So I'm just going to do a over b. So this becomes 1 over n squared minus 100n plus 4 all over 1 over n squared. We simplify here, right? Did you guys ever learn outers over inners?
I believe I know what you're
You guys
talking about.
learned
but, like,
that
I
keep
never
change
used it.
flip nonsense, right?
Oh yeah.
Whatever. Okay, whatever. N squared over n squared minus 100n plus 4. Oops, almost forgot my limit. This is going to equal, essentially I'm going to divide everything by n squared. So I get 1 over 1 minus 100 over n plus 4 over n squared. Take the limit as n goes to infinity. And this becomes 1, right? Because as we go to infinity, this goes to 0. This goes to 0. You're left with 1 over 1.
Yeah.
So what just happened?
Is that a finite number?
Yeah, this is the first case, right? Since L is finite, and we know that B sub n converges, what can we say about A sub n?
The auto converges
Why?
because of the limit comparison test.
And that is your write-up. So requires a little more work than DCT, right? Clearly. Requires a little more work than DCT, a little bit more writing, which is why people like DCT a lot more than LCT, but the downside is DCT does not always work. Okay? That's the point I was trying to get to. Any questions on the write-up? Any questions on the work? Any questions on, I don't know, anything?
John, for the quiz tomorrow, if we do LCT, do you have to carry the limit all the way down, or can we just
Absolutely, man. Your work does not make sense if you get rid of the limit. Come on.
Because like what's it called? I used to do is I would write it once, and I would do everything vertical and just like do an arrow all the way down to the end.
Oh, you're one of those people. Come on.
I mean, like, you know, it's to save time,
You're
dude.
older.
It's
You're older
more
now.
work.
Come on, grow up. You're not in high school anymore, right? Any other questions on? So once again, definitions are so important. Definitions are so important. Setup for this one, right? Doesn't matter. You can do A over B or B over A because you'll still get to the same conclusion. And then don't forget about your write-ups. Let's move on to the next thing.
Ratio something.
No, that's the next thing.
Okay.
We are moving on to 10.4. 10.4 talks about absolute / conditional convergence. It sounds a lot worse than it is. I promise you. When I learned absolute and conditional convergence, it took me a while to understand it because no one ever like told me like what it really is, and I was just like, oh, that's easy, right? So absolute / conditional convergence. Well, what do you think of when you hear the word absolute in math?
Like the absolute value. Or
Yeah,
something?
you think of
Yeah.
absolute value, right?
Yeah.
Just think of it like that in terms of series now. When you think of absolute value, what happens?
And it's
There's no
all
sign.
goes positive.
It turns whatever is on the inside positive, right? It's the washing machine or whatever, right? Or I don't know. If you
Mhm.
put dirty clothes in, it becomes clean. If you put clean clothes in, it becomes clean. Whatever. But it just means we're talking about positive terms. And if you haven't noticed, in 10.1 and 10.1, okay, maybe in 10.2 and 10.3, with these tests that we've just learned, they've all really been positive, haven't they?
Yeah.
Yeah.
Right? So now we just so what they did was they said that if you can prove convergence on a positive series, then you can say that it converges absolutely. So that's what absolute convergence is, right? So absolute convergence, it's basically if this converges, if you have a series and it's all positive terms, then without the absolute value signs, if you were to take them off, you can say that this converges also. And it's a pretty important theorem because it leads into negative stuff. So let me see an example here. Okay.
Wait,
So
I have a quick
let
question
me show
then.
you a quick, yeah, what's up?
Wait, then if you go to the previous problem, the like 1 over n squared minus 100n plus 4, and then you just put in absolute value, right? And then it turned into 1 over n squared plus 100n plus 4.
No. Nope, that's not how it works. It turns the terms positive. It does not turn the definition positive. It doesn't turn
Okay.
all the. That's not what I was saying. Okay. I think this will help. With series, there's a very popular thing that's used. Don't freak out when you see it. Or maybe some of you have seen it already. But this thing has a special name. It's called. Why didn't that come out in red? There we go. It's called an alternator. Why do you think it's called an alternator?
Because you could alternate with it.
Okay, next
You
try.
get-
What are the terms going to look like? What's the first term here? If I plug 1 in, I get
Zero.
You get
One
1.
over 1 squared. And then if I plug 2 in, I get
Is to always make it positive? Actually, no.
2 over 2 squared, I'm guessing. Yeah.
What do you guys notice? Oh shoot! Sorry. The top's
Wait,
always 1. The top's always 1.
Oh.
What do you guys notice?
Switching sign?
Yes, and this is why it's called the alternator, because it alternates the sign from turn to turn. Okay, it's a very, very popular term. And what this means is now we are playing with negative terms. This is what I meant, right? Like before we weren't really playing, we were just playing with positive terms mainly. But now we're going to come across these negative terms and we want to know, well, do we use the same thing to like prove them? Do we use something different? Yada, yada, yada. So this theorem that I just said about absolute convergence, we can kind of apply it to situations like this here, right? It says if without the alternator, if the series converges, then with the alternator, it will converge as well.
Okay.
See what I'm saying? So if this is my a sub n, right? If I look at a sub n with absolute values, what that actually does is it's going to get rid of all the negative terms, right? It's going to make all the terms positive. So what you end up getting is 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared, so on and so forth. You get the sum of 1 over n squared, right? And we know how to prove convergence on this one. This is
A p-series.
so this converges by p-series. So using this in conjunction with the definition I just said above, right? This guy right here, we can say since the absolute value, since this converges, the sum of, what is it? -1 to the n minus 1 n squared converges absolutely. Oh, I think I mixed that up. Sorry. We just say that the second piece converges. So since this converges, sorry, I was supposed to say that here, because we put absolute values on it, right? So since the absolute value of a sub n converges absolutely, we say that without the bars, it converges.
Okay.
Let's kind of make sense of this, right? Why would that work? Why do you think this works? Like look at the relationship, like term to term. Look at the relationship. Can you guys come to a conclusion?
Oh, because it's every time it subtracts, it's smaller than how many times?
Okay. Keep going.
So
Oh.
so it's increasing. The whole thing is increasing.
Oh, I thought you had it.
Dang.
So is it
so
like
the negatives are gonna be 0. They're gonna.
is it like constant?
It's gonna be 0.
It all follows the same idea. Look, we just said this thing converges, right?
Oh, that means since 1 over n squared is larger, then am I going the right ballpark?
Finish your sentence, man.
Yeah,
What's larger? What's larger than what?
1 over the absolute value of a sub n is larger than a sub n.
Yes.
And since the absolute value of a sub n converges, that means the a sub n has to also converge.
Yes, exactly. Oh my gosh. Did you guys get there? Do you guys see what he said? What this is saying is this is always going to be greater than or equal to this. Right? If I had a series with some negatives in it, well, that takes away values from the series. So if I have something that's smaller, and I know that without the negatives, it's bigger and converges, then I can say, right? It's just like another direct comparison almost.
Yeah.
Isn't it?
It always leads
Pretty
back to
much.
direct comparison.
Yeah. So that's pretty much the idea behind it. All right. Let me talk about the AST. AST is the alternating series test. And this is more of like a broader way to go about alternating series. So, and there's a lot of stuff that really pertains to alternating series tests, but there's a lot that we probably won't be able to get to, unfortunately. I'll put something in the video where, what is it? Like where there's some more application purposes of AST that you will come across in the fall, but not here. So alternating series test, okay? Obviously, or hopefully this is obvious, use only on alternating series. Okay, which means anything with an alternator. So as soon as you see an alternator, I know I'm using the AST. Does that make sense?
Yeah.
Okay, so here we go. AST. I'm on page 587. Okay. I just realized I don't like their definition. So given an alternator, and I'll call this A sub n. So given an alternating series, you need to check for two things, kind of like the integral test. And in fact, it's almost like similar to the, it's very similar to the integral test, but you need to check for two things, okay? If A sub n, oh shoot, what's the first one? Oh, plus one is greater, no, less than A sub n. And then if the limit as n goes to infinity of A sub n has to equal 0. So what is the first part saying? It's saying if it's decreasing. If the fifth term is smaller than the fourth term, is smaller than the third term, is smaller than the second term, and so on and so forth, right? So if the terms are decreasing and the limit of the sequence, not the series, is going to 0. Still with me?
Yeah.
Then, and only then, you know that the series is convergent. So once again, the terms need to be decreasing, the terms need to go to 0. If they don't go to 0, if they do not fulfill one of those two things, then it does not fail the AST. It's inconclusive. You got to use something else. Any questions? No? So let's look at a really easy example here, right? One that should look very familiar. So does that look familiar?
Yeah.
We saw this when we were doing the integral test, right? It just without the alternator, right? We said that 1 over n diverges. It's the harmonic series, and it diverges because when you integrate it, you get like ln and ln grows, right? So let's talk about what happens when we put an alternator on it, right? Because this is going to be like 1 minus a half plus a third minus a fourth plus a fifth, so on and so forth, right?
Yeah.
So with this, we're going to use AST. What gave it away? The alternator.
The alternator.
Yes, right. So this means need AST. So one, I'm going to show, honestly, just like the integral test, you can just state this one, the decreasing one. So it is decreasing. That's fine. Like you don't have to prove decreasing on this one. I think that's a little too much. Like you can clearly see that the terms are getting smaller and smaller, right? And then 2, well, this one's pretty easy, right? Taking the limit of just the sequence part. I mean, just this part,
Yeah.
right? The not like ignoring the alternator. You're just taking the limit as this goes to infinity. Obviously, this one goes to 0. So that works out too. So we can say by AST, the series converges. I don't know why I put an exclamation point. Math makes me excited. Sorry. Okay. And that's it. That's AST. AST is pretty easy, right? You just, if you're given an alternator, I mean a series with an alternator, just check if it's decreasing, check if it goes to 0. If it fills that, it's convergent. I kind of want to take this a step further though, and kind of make sense of what we what we like just did though, because this is a pretty interesting example. I just said it, right? We said that 1 over n diverges, but 1 over n with an alternator converges.
Oh,
Do you guys notice that, right? 1 over n, so 1 over n like grows too fast, right?
mm-hmm.
So what we can kind of conclude is that with the alternator, it's like it's taking away from the sum enough for the numbers to like converge into a number. Do you guys see what I'm trying to say here?
Yeah.
Like what's happening is like so here's one. Let me, if I sketch this out. So like at 1 it's 1, at 2 it's -1. Oh, come on. Oh, she's dead. Oh, there we go. Okay. At 2 it's -1/2. At 3 it's a +1/3. At 4 it's a -1/4. At 5 it's a +1/5, and so on and so forth, right? And what you guys can see is like the reds are like taking enough away from the blacks so that like it actually brings you to like a finite number. It like saves you from going off to infinity, you know? Isn't that crazy? I don't know. I thought that was pretty interesting. Dang, I wanted to do a lot more stuff. But that's pretty much it. I think I hit all the main points. AST, we only have the ratio test left, and it's something called power series. And then that should be your next quiz 3, not the one tomorrow. All right, but I'll stop here. I'm a little over time. I'm sorry. I'll put up a video. Honestly, the video you technically don't need to watch, which means like no one's gonna watch it. You technically don't need to watch, but it's good to like save these videos for the fall. I'm just letting you guys know, like just in case like
It's like review the videos over August and everything.
Yeah, so this particular video you will absolutely cover in the fall, and you will need to know how to use it. It's the it's how to use it's called the alternating series error bound. Like it tells you how off you are from the actual sum. You guys will be doing this stuff in the fall, but not here, for obvious reasons. Okay, so definitely check it out if you have time over the summer. I don't know. I mean, you're gonna have time, right? Because you're gonna be indoors and nothing like me. So
the quiz is only gonna encompass all the like the theory test all the way to the alternating theory. Not
okay. Oh, you weren't here in the beginning. The stuff we did today is not on the quiz tomorrow.
Oh, okay.
The quiz tomorrow, it's going to be sequences and geometric series. I put it up here.
So is it going to be all the way to limit comparison?
No, up to the direct comparison test.
Oh, okay.
All right. Guys, please, I'm looking for properly justified write-ups. So please make sure your write-ups are good. Hey, if you want to like message me, I'm sorry, Kim, I don't know what happened. The message, I wasn't alerted, but if you message me and you're like, is this okay for a write-up? By all means, like do that, like show me and I'll help you out, you know? There are some practice problems I would probably check out at the end of section 10.3, which is page 583. So check out page 583 for extra examples or like practice. It's numbers, I don't know, like 47 to like 70. I'm not telling you to do all of them, right? But definitely look at one and think about, well, how would I do this problem? Which tests that we've done so far would I use? Do I need to use LCT on it? You know, like things like that. You know, like so. Definitely try some of these practice problems. There's a bunch you can find online. Just type in, you know, practice, you know, series problems with convergence and divergence. There's so many out there. And like, if you want to do like a practice write-up and just like message me on like privately on GroupMe and be like, hey John, is this okay for a write-up? Do it by all means. All right. But yeah, your quiz is tomorrow. Let me know if you guys have questions, and I will see you on Wednesday. Good luck on the quiz.
John, quick question.
Yeah.
Could you scroll down for me, like all the way when you were doing the AST? So if you scroll up just a little bit, like where you were showing what each number was,
Mm-hmm.
when you know how it's 1 minus half, isn't it supposed to be like -1
Oh,
plus a
damn it.
half minus?
Yeah,
That's what
yeah,
kind of threw me off.
yeah. That should fix it.
Okay, gotcha.
Any questions on the test, about the test? Any questions in general? If not, you guys can go.
John, so for the